Okay, so we talked about dissociation constants of acids and bases in last section. Now we're going to look at a special case, the dissociation of water. You may recall that water acts both as an acid and a base. It acts both as an acid and a base, right? And so in this case, if this is the first water molecule, let's call this molecule number 1, and this will be 1 here, this is 2, and this is 2 here. Can you see that 1 is accepting a blue sphere from 2, right? Because 2 starts out with 2 and goes to 1. 1 starts out with 2 and goes to 3, right? So you can see this is acting as a base, and this one is acting as an acid because it's donating an H plus ion, right? So, and that's exactly what happens. Water acts as an acid and a base, and it's called autoionization. Autoionization is what it's called. I don't have that word on here, but we're going to see what we can learn about pH by appreciating the autoionization of water, where water, liquid water, and liquid water actually make the conjugate acid and the conjugate base of the respective water molecules. Okay, so the learning goal here is to use the water dissociation constant expression to calculate the concentrations of hydronium ions and hydroxide ions in aqueous solution. All right, so we said before, water is amphoteric. That is, it acts as a water and as a base. And we saw from the previous slide that an H plus is transferred from one water molecule to another. One water molecule acts as an acid, one acts as a base. Okay, and equilibrium is reached between the acid-base pairs. All right, and so what that means is this reaction goes both ways. It goes that way and it goes this way. And that's what this arrow means, right? You can imagine that water is a very weak base and water is a very weak acid, right? So it doesn't go much that way, but it does go some. And if this is an acid, this is its conjugate base because that is the same water molecule but with the H plus stripped off. All right, so it turns out that we know what the water dissociation constant is because we've measured it. It is 10 to the minus 14. 1 times 10 to the minus 14. That is the acid dissociation constant for water at 25 degrees Celsius. All right, and that, in other words, well, I actually didn't write the expression for you. Let's do that. Did we have that on the previous page? No, we didn't. Okay, let's write the expression. It's K is equal to products over reactants, right? Products over reactants, right? We've done that a couple times, which is equal to the concentration of, there's 1-on-1 product. There's my other hydroxide, right? And look, these are both pure liquids. So we don't put either of them in the denominator. The denominator is simply 1. And when the denominator is 1, we typically don't even write a denominator, right? So let's leave it like that. Kw, this is a special case of the acid dissociation, so we're going to call Kw. Kw is equal to the product of these two. And that's what I've got right here. Kw is equal to the product of those two. And so therefore, since this is 1 to 1, if this is 10 to the minus 14, that means that each of these is 10 to the minus 7. Right? All right, so the ion product constant for water is defined as blank. The product of the concentrations, we've already got that. It's equal to blank. All right, and so let's go down to these points here. When they're equal, the solution is said to be neutral. Okay? When this is greater, the solution is said to be acidic. When this is greater, the solution is said to be basic. All right? This and that. My language apparently is getting a little tired. And just pointing and grunting now. All right, so let's look at this. What can we do with this? If we know that it's 10 to the minus 14 at 25 degrees Celsius, we know that. That's what the definition is, okay? If we know that, and we know one of these, we can figure out the other, okay? Because it's just algebra, right? So if these are both 10 to the minus 7, then you multiply them together and you get 10 to the minus 14. That's what we said in a previous slide, right? If they're both 10 to the minus 7, then we say they're equal to each other, and we say that it is neutral, okay? If one of them is greater, looks like we've got an acidic solution here because the acid is in greater concentration, it's higher. If it's greater, then the hydronium ion concentration is going to be greater, right? That's if it's acidic. It's going to, the concentration of H3O plus is going to be greater than that number, and it's going to decrease the hydroxide amount. And we would say that it's acidic. You know where we're going with this, right? What if we add base to pure water? Then we would say that the hydroxide ion concentration is higher, and that causes it to be greater than 10 to the minus 7, and it's going to decrease the hydronium ion concentration, and we would say it's basic. All right, so we already showed you this picture in a previous slide. I think we're basically done. Let's do a calculation here. Table 11.6. I don't think I want to go over with you right now. It's sort of yes I do. If it's neutral, the concentration of acid is this, the concentration of base is that, and you multiply them together and you get 10 to the minus 14. If it's acidic, let's say it's really very much acidic. We have a high concentration. Wait. That would be a high concentration of acid, right? Well then, since this is constant, this must be much smaller, right? And if you multiply 10 to the minus 2 times 10 to the minus 12, you get 10 to the minus 14. You get where I'm going with this, right? If the concentration of hydronium is very small, then the concentration of the hydroxide must be larger because this is constant, right? Multiply these two numbers together, and you'll see that this times that is equal to that. And that's just a consequence of our expression, Kw is equal to the concentration of hydronium times the concentration of hydroxide. So let's do an example. What is the hydronium ion concentration of a solution if the hydroxide ion concentration is 5 times 10 to the negative 8? So what we're going to do is we're going to say Kw is equal to the one times the other. This is just a definition, right? And we know what Kw is. It's 10 to the minus 14, right? And we know what this is. It's 5 times 10 to the minus 8. But what we don't know is what this is. That's what we're being asked. So what do? I just divide, right? We solve for x. So 10 to the minus 14 over 5 times 10 to the minus 8. Let me say 1 times 10 to the minus 14 is equal to that circle there. I'm going to do this in my head. 10 to the minus 14 over 10 to the minus 8 is 10 to the minus 6. And 1 divided by 5 is 0.2, right? It's 1/5. And so we're going to say this is 2.0 times 10 to the minus 7. All right, there is your answer. And I encourage you to get your calculator, put those numbers in your calculator, and go do that and verify that. All right, so let's do one more. Here's a learning check. Please pause the video and check it and make a guess, not a guess, work it out, and then come back and compare your answer against mine. Okay, so I'm going to suppose you paused it. I'm going to, first of all, write the definition down. I'm going to do this probably every time because it helps me orient myself. You ought to consider using this as a problem-solving strategy yourself. Writing down the definition. If lemon juice has a concentration of that, what is the hydroxide ion concentration? So you have to know what Kw is, but we do. It's 1 times 10 to the minus 14, right? And we know this is 2 times 10 to the minus 3. And we're being asked, what is the hydroxide ion concentration? This is no problem. I just divide both sides by 2 times 10 to the minus 3, right? So 1 times 10 to the minus 14 over 2 times 10 to the minus 3 is equal to the hydroxide ion concentration, right? And so this is 1/2 times 10 to the minus 11, right? Which is equal to 0.5 times 10 to the minus 11, which is equal to 0.5 times 10 to the minus 12. And there it is, 0.5 times 10 to the minus 12. All right, hope that's helpful. We'll get more chance to practice this kind of math in the next conversation.